Today we're going to be doing sample and distribution models for sample means. Suppose we have the height data from a random sample of 95 high school students. So I'll show you the data in a minute. We will consider this our population of height data. For this population, mu is 66.54 and sigma is 3.857. So we have a random variable, e of x equals mu, standard deviation equals sigma, and our variance is sigma squared. So here we have the height data of 95 high school students. We will consider this our population of height data. So with, like I said, mu equals 66.547 and sigma equals 3.856. So why are we using mu and sigma here and not x bar and s? And the reason why we're using mu and sigma here is this is because it's from a population. This is our population data, not our sample data. So let's go back and derive our expected value of x bar, our variance of x bar, and our standard deviation of x bar. Okay, so in order to do this, our expected value of x bar is our expected value of x1 plus dot 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 plus all the way to xn, all divided by n. Then we can factor out that 1 over n and times the expected value of x1 plus dot 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 all the way to xn. And we know that our expected value of x is equal to mu. So this would be 1 over n times n and mu, because it's times that. Our n's cancel out, and this would be mu. Therefore, our expected value of x bar equals mu. So with variance of x bar, it would be the variance of x1 plus all the way to xn, all divided by n. Since variance is squared, I can factor out that 1 over n squared. And this would be times the variance of x1 plus dot 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 the variance of xn and this would equal 1 over n squared times sigma squared plus sigma squared. This would then equal 1 over n squared times n times sigma squared. Our n's cancel. So our variance of x bar ends up being sigma squared all over n. So these are two formulas that you'll need to know so far. So we have our expected value of x bar is mu, and our variance of x bar is sigma squared over n. Then our last one, the standard deviation of x bar is just the square root of the variance of x bar. So this would be the square root of sigma squared over n, which would just be sigma over the square root of n. So that is another one that you will need to know. So to make use of the sample and distribution model for x bar, certain assumptions must hold true. We will check conditions as a way to determine whether the assumptions are reasonable. So our assumptions are sample values are independent of one another. If the sample is drawn without replacement, check the 10% condition. And the sample size is large. And in order to see if the sample size is large, we need to check the conditions below. First, condition to check is the random sample condition. Sample should be a simple random sample of the population, unbiased sample and method, and sample representative of the population. Check for independence. Then the 10% condition. Sample is less than or equal to 10% of the population. Large enough sample size condition. With a large enough sample size, we can use a normal model for the sample and distribution model of X bar. Usually n is greater than or equal to 20 is a good rule of thumb. This comes from the central limit theorem, the fundamental theorem of statistics. You don't always need a large sample size. If the sample size isn't large, but the original population is approximately normal, then the sample and distribution for the model of X bar is also approximately normal. In fact, you will check this first before you check the sample size. So we have a distribution with the following. Our center is our expected value of X bar, which is mu of X bar, which is just mu. Our shape is approximately normal under certain conditions. And our spread, our standard deviation of X bar, or sigma of X bar, is sigma over the square root of n. Let's go ahead and look at a couple of examples. The first example here. A study of college freshmen study habits found that the time, in hours, that college freshmen use to study each week is approximately normally distributed, with a mean of 7.2 hours and a standard deviation of 5.3 hours. What is the probability that a randomly chosen freshman studies more than 15 hours? So we need to find the probability that x is greater than 15. In order to do that, we need to first find the z-score. So to find z, we need to remember that it's x minus mu all over sigma. So this would be 15 minus 7.2 all over 5.3. This would give us 1.47. So if I were to draw this, we would have 0 as our mean, 1.47 here. We would be finding this area over here. So this is the probability that z is greater than 1.47. Using your calculator or your table, you should get about 0.0706. So about 7.06%. What are the mean and standard deviation for the average numbers of hours, X bar, spent studying by a simple random sample of 55 freshmen? So first we need to check the conditions. We're told that the sample is a simple random sample, so our conditions told that it's a simple random sample of 55 freshmen. 55 freshmen is less than 10% of all freshmen. So that's our 10% condition. And the population distribution of freshmen is approximately normal. Or we could say n equals 55 is greater than or equal to 30. So by the central limit theorem, our sample and distribution is approximately normal. So our n, 55, Okay, so we need to find mu of x bar, which equals mu, which is 7.2. And we need to find sigma of x bar, which equals sigma over the square root of n, which is 5.3 divided by 55, divided by the square root of 55. And that equals 0.715. So we found our mean and standard deviation for the average number of hours for 55 freshmen. And then lastly, see what is the probability that the average number of hours spent studying of a simple random sample of 55 freshmen is greater than 8 hours. So this is the probability that x bar is greater than 8. So what we need to do is we need to find our z-score. So z would be 8 minus 7.2 all over 0.715. That gives us 1.12. Draw a quick picture of that. So we would have that there. And using our calculator, when we're finding z is greater than 1.12, we would get 0.1315. So the probability would be about 13.15%. Let's look at one more example. This one says the scores of students on the ACT college entrance examination in a recent year had the normal distribution with mean 20.4 and standard deviation sigma of 5.8. A, what is the probability that a randomly chosen student scored 24 or higher on the ACT? So we need the probability that x is greater than or equal to 24. So go ahead and find here, they tell us that mu is 20.4 and sigma is 5.8. So we need to find our z-score, which is x minus mu all over sigma. Z here is x is 24 minus 20.4 all over 5.8, and that gives us 0.62. So this looks like I have 0.62. So this would be the probability that z is greater than 0.62. Using our calculator, normal CDF again, we would have 0.2674. And then B, what are the mean and standard deviations of the average height or the average ACT score? For X bar, for a simple random sample of 30 students. So first we need to check our conditions. One, it's a simple random sample of 30 students taking the ACT. Second, the population distribution of the ACT scores is normal. Approximately normal. So our sampling distribution model is normal. And then to go ahead and find this, mu of x bar equals mu, which is 20.4. Sigma of x bar, which would be sigma over the square root of n, which would be 5.8 over the square root of 30, and that gives us 1.06. And then C, what is the probability that the average ACT score of a simple random sample of 30 students is 24 or higher? So we need the probability that X bar is greater than or equal to 24. So we need to go ahead again and find our Z-score. So that would be 20.24 minus 20.4. So X minus mu all over sigma divided by the square root of n. Which was 1.06. And this gives us 3.40. So we need the probability that Z is greater than or equal to 3.40. We go ahead and put that in our calculator, and that would be 0.00034, which makes sense because that's greater than 3 standard deviations from the mean. Because if I were to draw this, here's 0, 3.44 would be over here. So it's not much under the curve.